Picture standing on the surface of a distant world where the sky doesn't just hold one sun but two. As you watch, the horizon glows with twin flames dipping below the edge of the planet, casting long, interwoven shadows across an alien landscape. The air hums with an eerie, golden light, and for a moment you're struck by the sheer strangeness of it all. This isn't the stuff of science fiction, it's a real possibility in the vast tapestry of our universe. Binary star systems, where two stars orbit each other in a cosmic dance, are actually more common than single star systems like our own. And that raises a tantalizing question. If life emerged here under one steady sun, could it also thrive in the chaotic, radiant embrace of two? The idea of life in binary star systems isn't just a wild speculation. It's a puzzle that challenges everything we know about habitability. Imagine the extremes, worlds tugged by competing gravities, bathed in erratic light, where temperatures could swing wildly between scorching heat and freezing cold. At first glance, it seems inhospitable, a place where life would struggle to take root. But nature has a way of surprising us. Life on Earth thrives in the deepest oceans, the harshest deserts, even in the radioactive aftermath of nuclear reactors. If life can adapt to those extremes, who's to say it couldn't find a way under twin suns? This is where the science gets thrilling. Researchers are uncovering clues that double star systems might not just host life, they could actually create unique niches where it flourishes. From planets locked in stable orbits between two stars to moons swirling around gas giants in far-off habitable zones, the possibilities are as vast as they are mesmerizing. And the implications, their universe-shaking, finding life, or even the potential for it in such extreme environments would rewrite our understanding of biology, chemistry, and the very definition of a habitable world. So let's dive into the mesmerizing science behind binary star systems, where the rules are different, the challenges are extraordinary, and the discoveries waiting to be made could change everything we think we know about life beyond Earth. Binary star systems are cosmic duos, two stars bound together by gravity, locked in an endless orbital waltz across the cosmos. Far from rare, these stellar pairs dominate the galaxy. In fact, astronomers estimate that over half of all star systems in the Milky Way contain at least two stars, with some even hosting three or more. That means our solitary sun is actually the exception, not the rule. These systems come in different flavors, each with its own quirks. Close binaries are like cosmic tango partners, stars so near to each other they share atmospheres or even swap material, creating dazzling stellar phenomena like novas or accretion disks. Then there are wide binaries where the stars drift apart like old friends, keeping a comfortable distance, orbiting each other over spans that could take thousands of years. And don't forget eclipsing binaries, the celestial show-offs. From our vantage point, these stars periodically pass in front of each other, causing dramatic dips in brightness that make them a favorite for astronomers studying stellar properties. The gravitational dynamics in these systems are a far cry from the orderly simplicity of single star systems like ours. Here, planets follow predictable, stable orbits around one central sun. But in a binary system, it's a gravitational tug-of-war. Planets might orbit one star, both stars in a wide loop, or even trace figure-8 paths between them. This constant push and pull creates extreme environments, worlds where gravity stretches and squeezes, where seasons might shift unpredictably, and where the very definition of a year becomes fluid. Yet, against all odds, some of these chaotic systems could still cradle life. The universe loves a challenge, and so do we. In a single star system like ours, the habitable zone is a straightforward concept, a comfortable band of space where temperatures are just right for liquid water to exist on a planet's surface. But drop a planet into a binary star system, and suddenly the rules change dramatically. Instead of orbiting a single sun, worlds here must navigate the competing gravitational pulls and light intensities of two stars. This creates habitable zones that aren't fixed but dynamic, shifting, overlapping, or even forming entirely new regions where conditions might still support life. Take the case of a planet orbiting both stars in a wide binary system. Here, the habitable zone isn't a neat ring. It's more like a shimmering, evolving shell. As the stars move in their orbits, the zone wobbles, stretching closer to one star and then the other. A planet situated just right could experience seasons driven not by axial tilt, but by its changing position relative to each star's warmth. Some models even suggest these shifting zones might create sweet spots, regions where, despite the chaos, temperatures stabilize long enough for liquid water to persist over geological time. Then there's the fascinating scenario of planets orbiting just one of the two stars. In these cases, the second star acts like a distant but influential neighbor. It might not provide much heat, but its gravitational pull could stabilize or destabilize the planet's orbit, indirectly shaping the habitable zone. Some simulations show that under the right conditions, these single-star orbits within binaries can be even more stable than our own solar system, offering surprisingly cozy niches for life to emerge. But the real showstoppers are the circumbinary planets, worlds that orbit both stars at once. Picture a planet tracing a grand, lazy loop around its twin suns, basking in their combined glow. These systems create what scientists call binary habitable zones, where the overlapping warmth of both stars carves out a region where liquid water could exist. The trick is finding the right distance too close, and the gravitational tug of war would rip the planet apart. Too far, and the star's combined light would be too faint. Yet, when the balance is perfect, these worlds could enjoy a double sunrise every morning, with climates moderated by the interplay of both stars' energy. What makes these scenarios so compelling is how they challenge our Earth-centric view of habitability. On our planet, life thrives under predictable cycles of day and night, summer and winter. But in a binary system, the rhythms could be wildly different: extended twilight periods, irregular seasons, or even days where the suns eclipse each other in dazzling displays. Yet, if we've learned anything from life on Earth, it's that biology is endlessly adaptable. From bacteria surviving in acidic hot springs to creatures thriving in crushing ocean depths, life finds a way. In the kaleidoscopic environments of binary star systems, it might just find ways we haven't even dreamed of yet. The dance of planets in binary star systems is a breathtaking display of cosmic physics, one where gravity becomes both architect and disruptor. Unlike the orderly, near-circular orbits we see in our solar system, worlds in double-star systems face a far more complex reality. Some cling tightly to just one star, like a moon tethered to its planet, while others loop around both in vast, sweeping arcs. The key question isn't just whether these orbits are possible, but whether they can last long enough for life to take hold. Take circumbinary planets, the real-life counterparts to Star Wars' Tatooine. These worlds don't orbit a single star, they circle both, tracing paths that might resemble a stretched-out figure 8 or a wobbly ellipse. At first glance, this seems like a recipe for chaos. With two massive gravitational forces tugging at them, how could these planets avoid being flung into space or crushed into their stars? The answer lies in a delicate balance. For a circumbinary orbit to remain stable, the planet must stay far enough away that the star's gravitational pulls blend into a single, unified force. Think of it like walking a dog with two leashes. If you hold both taut and evenly, the tension cancels out, creating a steady path. Too close, though, and those competing tugs send everything spiraling. Remarkably, astronomers have already spotted planets pulling off this feat. Kepler 16b, the first confirmed circumbinary planet, orbits its twin stars every 229 days, basking in their combined glow. Even more intriguing, its orbit has remained stable for over 1 billion years, proof that under the right conditions, binary systems can offer surprising sanctuary. But not all planets in these systems take the circumbinary route. Some orbit just one star, with the second acting as a distant but influential companion. Here, stability depends on distance. If the second star looms too close, its gravity can yank the planet out of orbit over time. But in wide binary systems where the stars are separated by vast distances, a planet might enjoy a nearly normal life, just with an extra, faint sun lighting up its night sky. Proxima Centauri b, for instance, orbits one star in a triple star system, yet simulations suggest its climate could be surprisingly temperate despite its chaotic stellar neighborhood. The wildest orbits emerge in tight binary systems, where stars whirl around each other in days or even hours. Planets here face extreme forces, tidal stretching, violent temperature swings, and gravitational shocks. Yet even in these frenetic environments, stability isn't impossible. Some models show that planets can settle into resonant orbits, moving in sync with the star's dance, like a surfer riding the same wave indefinitely. Others might find refuge in Lagrange points, gravitational sweet spots where the pulls of both stars cancel out, creating islands of calm in a stormy cosmos. What's truly astonishing is how often nature finds these equilibriums. Binary star systems shouldn't, by classical logic, be friendly to planets. Yet we've discovered dozens of worlds thriving in these extremes, some rocky, some gaseous, a few even perched tantalizingly in habitable zones. Each one defies expectations, proving that stability isn't just about simplicity. Sometimes it's born from chaos itself. Life under twin suns wouldn't just mean double the daylight. It could mean enduring roller coaster temperature swings that make Earth's seasons seem tame by comparison. Imagine a world where daylight brings the blistering heat of two stars blazing overhead, only to plunge into frigid darkness as both suns dip below the horizon. Without the steady, predictable rhythm of a single star, planets in binary systems could experience temperature spikes and drops so extreme they'd rewrite the rules of habitability. But here's the twist: nature has a few tricks up its sleeve to soften these extremes, and they might just make life possible after all. The root of these wild fluctuations lies in the way dual suns deliver energy. In a single star system like ours, sunlight arrives at a relatively constant rate, with variations tied mostly to a planet's orbit and tilt. But in a binary system, the heat input can change dramatically depending on the star's arrangement. Some planets might bask under both suns simultaneously, their surfaces bombarded by intense radiation. Others could experience alternating periods of single and double sunlight, creating a jagged temperature graph with peaks and valleys sharp enough to crack rock. And if the stars are different types, say, a blazing blue giant paired with a cooler red dwarf, the heating becomes even more erratic, like swapping between a blowtorch and a space heater at random intervals. Yet some worlds might find balance in their atmospheres. A thick, insulating layer of gases could act like a cosmic thermostat, absorbing excess heat during scorching dual-star days and slowly releasing it through the long, cold nights. Venus, for instance, shows how a dense atmosphere can smother a planet in relentless heat. But in a binary system, that same greenhouse effect might instead stabilize temperatures, preventing the kind of wild swings that would boil oceans by day and freeze them solid by night. Even a thinner atmosphere with the right mix of gases, water vapor, carbon dioxide, methane could smooth out extremes, creating pockets of relative calm where life might cling on. Then there's the role of planetary tilt or axial inclination. Earth's 23-degree tilt gives us predictable seasons, but in a binary system, things get complicated. The gravitational tug of war between two stars could cause a planet's axis to wobble chaotically, leading to erratic climate shifts. Or, in a stroke of cosmic luck, That same interplay might lock the tilt into a stable resonance, creating seasons that, while unusual, follow a pattern life could adapt to. Picture a world where summer arrives when both suns align in the sky, bathing the planet in relentless light, while winter brings a twilight haze as one star dominates and the other lingers on the horizon. Even the planet's rotation could play a role. A slow, lazy spin might mean one side cooks under perpetual daylight while the other freezes in eternal night, a scenario familiar from tidally locked exoplanets. But if the world spins fast enough, the heat could distribute more evenly, like a rotisserie chicken turning steadily under a grill. Some binary system planets might even experience temporary tidal locking, where one star's gravity briefly halts their rotation, only for the other star to kick it back into motion. The result, climate zones that shift over centuries, forcing life to migrate or evolve at a breakneck pace. What's fascinating is how these extremes might actually fuel biodiversity. On Earth, the harshest environments often host the most resilient life forms, extremophiles thriving in boiling geysers, frozen tundras, or acidic pools. In a binary system, organisms could evolve to exploit the temperature swings, becoming dormant during scorching peaks or freezing lows, then bursting into activity during brief, golden intervals of moderation. Others might develop reflective coatings to deflect daytime heat or insulating layers to survive the cold, turning survival into an art form. The deeper we look, the clearer it becomes. Binary star systems don't just create obstacles for life, they create opportunities. Yes, the temperatures can swing wildly, but with the right atmosphere, the right tilt, or even the right evolutionary creativity, life might not just endure under twin suns, it could thrive in ways we're only beginning to imagine. Imagine stepping onto an alien world where the sky pulses with the glow of two suns, not just illuminating the landscape, but reshaping it in ways that defy earthly logic. Here, weather isn't just a backdrop, it's a spectacle sculpted by competing gravitational tugs and dual sources of heat. Storms could rage with ferocity unseen on our planet, fueled by temperature differentials so extreme they make Earth's hurricanes look like gentle breezes. Picture winds howling at speeds that strip rock to dust, or rain that falls sideways as atmospheric pressure buckles under the stars' conflicting pulls. And then there's the light, not the steady glow of a single sun, but an ever-shifting tapestry of radiance, casting shadows that spiral and twist as the stars wheel overhead. One of the most striking features of these worlds would be their twilight zones, regions caught in perpetual half-light, where the suns never rise or set together. In some binary systems, a planet might orbit at just the right angle to keep one star perpetually near the horizon, while the other arcs high overhead. The result, a band of territory bathed in eternal dusk, where temperatures hover in a Goldilocks zone between scorching day and freezing night. Life here could resemble Earth's deep-sea ecosystems, where organisms adapt to minimal sunlight, or it might evolve entirely new survival strategies like photosynthesis tuned to the faint, blended glow of two distant suns. But twilight isn't the only oddity. Seasonal cycles in these systems could be utterly alien. On Earth, seasons follow a predictable rhythm tied to axial tilt and orbit. In a binary system, they might hinge on the stars' dance. A planet orbiting two closely paired stars could experience stellar seasons, periods where the stars' combined heat scorches the surface, followed by stretches where their light cancels out, plunging the world into a deep chill. Or consider a world where one star dominates for centuries, only to be overtaken by the second in a climatic revolution that rewrites the rules of habitability mid-stride. Then there's the question of storms. With two stars pumping energy into the atmosphere, weather systems could reach apocalyptic scales. Hurricanes might span continents, their fury amplified by the conflicting heat gradients of the twin suns. Lightning could crackle in constant planet-wide displays as charged particles from both stars collide in the upper atmosphere. Some models even suggest the possibility of hypercanes, storms so vast and powerful they reshape geology, carving canyons with wind alone. Yet amid this chaos, pockets of stability could emerge. Just as Earth's jet streams steer weather patterns, the complex interplay of binary stars might create stable atmospheric currents, rivers of air that channel heat and moisture in repeating life-friendly cycles. A planet with a fast rotation might spread the star's energy evenly, preventing runaway storms, while oceans could act as thermal buffers, absorbing excess heat by day and releasing it slowly by night. The real marvel is how life might adapt to these extremes. On Earth, organisms thrive in sulfuric acid clouds and sub-zero brine. On a binary world, evolution could cook up even wilder innovations. Creatures with reflective hides to deflect double sunlight, plants that track both stars across the sky, or microbes that lie dormant for centuries until the perfect alignment of suns triggers a bloom. Weather wouldn't just be a force to endure, it could become a rhythm to exploit, a calendar written in wind and light. What's certain is this: in binary star systems, climate isn't just a detail. It's the heartbeat of the world, pulsing to the rhythm of two suns, a reminder that the universe writes its rules in ways we're only beginning to decipher. In the delicate gravitational ballet of a binary star system, the forces at play don't just shape orbits, they reshape worlds. Tidal forces, those subtle yet relentless tugs between celestial bodies, become magnified under the influence of two suns. A planet caught in this cosmic squeeze doesn't simply rotate. It flexes, groans, and sometimes even fractures under the strain. Picture a world where the ground beneath your feet isn't solid and unchanging, but alive with movement, its crust buckling like a sheet of metal bent back and forth until it cracks. The mechanics of these tidal forces are deceptively simple in theory but devastating in practice. As a planet orbits its twin stars, the side facing one star feels a stronger gravitational pull than the side facing away. This imbalance stretches the planet, elongating it slightly toward the nearer star. In a stable system, this stretching might settle into a predictable rhythm, a constant, gentle flexing. But in tighter binaries, where stars whip around each other at close range, the effect intensifies. The planet isn't just stretched, it's kneaded like dough, its interior heating up from the friction of relentless gravitational massage. This isn't just hypothetical. We see tidal forces at work in our own solar system. Io, Jupiter's volcanic moon, is a textbook example. Squeezed by Jupiter's gravity and the tug of neighboring moons, Io's interior is so heated by tidal friction that it erupts constantly, its surface dotted with lava lakes and sulfur plumes. Now imagine that same process, but amplified by a second, equally massive gravitational source. A planet in a binary system could experience tidal heating so extreme its crust splits open like an overripe fruit, spewing molten rock across continents and filling the sky with ash. The consequences go beyond volcanoes. Tidal forces could lock a planet into a deadly embrace with its stars, slowing its rotation until one side permanently faces the binary pair. The sunlit hemisphere would bake under unrelenting heat while the dark side freezes into a wasteland. Atmosphere and water, if they existed at all, might migrate to the twilight zone between these extremes, leaving vast deserts of scorched rock and ice. Even more chilling is the possibility of tidal disruption, a fate where the star's combined gravity literally pulls the planet apart. We've observed this gruesome process in doomed comets that stray too close to stars, stretching into streamers of debris. For a planet orbiting too near to a tight binary pair, the end could come not with a bang but a slow, agonizing unraveling. Yet there's a flip side to this violence. Tidal heating could also be a lifeline. On icy moons like Europa or Enceladus, tidal forces create subsurface oceans, hidden reservoirs of liquid water warmed by friction. In a binary system, a planet with a thick ice shell might harbor similar oceans, kept liquid not by sunlight but by the constant churning of its core. These dark, warm seas could become incubators for life sheltered from the chaos above. The lesson here isn't just about destruction, it's about transformation. Tidal forces in binary systems don't merely stress planets, they redefine what a planet can be. Some worlds might crack under the pressure, while others, forged in that same crucible, could become stranger and more wondrous than anything we've yet imagined. The universe doesn't play by Earth's rules, and in the tug of war between twin suns, the line between catastrophe and creation is thinner than we think. The light pouring onto a planet in a binary star system isn't just doubled, it's remixed. Imagine standing on a world where the sky is washed in the deep crimson glow of a red dwarf, only for a second yellower sun to rise alongside it, flooding the landscape with an entirely different spectrum of radiation. This isn't just a visual spectacle, it's a biochemical puzzle. Life evolving under twin suns wouldn't just adapt to light. It would have to navigate a chaotic blend of wavelengths, each star competing to shape the very rules of biology. Take photosynthesis, the foundation of Earth's food chains. Here, plants and algae evolved to harness the specific wavelengths our sun emits most intensely, primarily blue and red light, with green bouncing off unused, which is why leaves appear green to our eyes. But drop Earth-like plants onto a planet circling a red dwarf and a yellow sun, and suddenly the game changes. Red dwarfs flood their planets with infrared and far-red light, while yellow stars like ours emit stronger bursts of blue and ultraviolet. An organism trying to photosynthesize here would face a brutal choice: specialize in one star's output and starve when the other dominates, or evolve a hybrid system capable of harvesting energy from both. Some scientists speculate that alien vegetation might develop broad-spectrum, pigments molecules capable of absorbing wildly different wavelengths, turning their leaves pitch black to soak up every available photon. Others might switch strategies entirely, leaning on geothermal energy or atmospheric chemistry when light becomes too erratic. And what about vision? On Earth, eyes evolved to match the sun's peak output, with most creatures favoring wavelengths around 550 nanometers, what we perceive as green-yellow. But in a binary system where the light spectrum shifts dramatically depending on which star is dominant, eyesight could take bizarre turns. Predators might develop multi-peaked vision, their retinas packed with photoreceptors sensitive to both the infrared glow of a red dwarf and the harsh blue of a yellow sun. Prey, in response, could evolve camouflage that shifts color under different lighting, blending into the landscape whether bathed in crimson or gold. Some creatures might even see entirely outside our visual range, perceiving heat signatures or ultraviolet patterns invisible to human eyes. The challenges don't stop at biology. The mixed light of binary stars could alter planetary chemistry itself. Red dwarfs are notorious for their flares, sudden eruptions of ultraviolet and X-rays that strip atmospheres and bombard surfaces with deadly radiation. Pair one with a calmer yellow star, and a planet might oscillate between periods of relative calm and violent sterilization. Life here would need shielding, thick atmospheres, subsurface refuges, or even biological armor like radiation-resistant cell walls. Alternatively, organisms could time their life cycles to the star's rhythms, blooming only during the yellow sun's dominance and retreating into dormancy when the red dwarf rages. Yet within these extremes lies opportunity. The overlapping light spectra could create niches Earth never imagined. Deep-sea equivalents might thrive in perpetual twilight, where the blended glow of both stars penetrates just enough to fuel life without scorching it. High-altitude ecosystems could evolve to harness ultraviolet light for energy, while cave-dwelling organisms recycle infrared into biochemical reactions. The sheer variety of lighting conditions might spur biodiversity beyond anything on Earth, with species partitioning themselves not just by geography but by spectral preference. What's clear is this: in binary star systems, light isn't just illumination, it's a sculptor, carving evolutionary paths we're only beginning to glimpse. If life exists under twin suns, it won't follow Earth's playbook. It'll rewrite it. The idea that life might hitchhike across the cosmos isn't new, but in binary star systems, the game changes entirely. With two stars orbiting each other, their gravitational dance creates highways for material to travel between worlds at speeds and scales unimaginable in our solitary solar system. Asteroids, comets, and even dust grains could act as interstellar taxis, ferrying microorganisms from one planet to another with startling efficiency. And here's the kicker: binary systems might not just make panspermia possible, they could supercharge it. Think of how material moves in our own neighborhood. When an asteroid strikes Earth, debris can be flung into space, but the odds of it reaching another habitable world are vanishingly small. Mars is our only plausible target, and even then, the journey takes millions of years. Now imagine that same impact in a binary system. The debris doesn't just drift into the void, it's caught in the intricate web of two stars' gravity, slingshot between them at velocities that could carry life-bearing fragments across interstellar distances in mere centuries. Some models suggest that in tight binary pairs, rocks ejected from one planet could reach another in as little as a few decades, fast enough for even delicate microbes to survive the trip. Then there's the role of stellar winds. Single stars like our Sun emit streams of charged particles that push material outward, but in binary systems, those winds collide, merge, and twist into complex magnetic highways. Dust and organic molecules riding these currents could travel far faster than they would under a single star's influence. We've even observed real-world examples. In the HD 2938 system, astronomers detected carbon-rich gas swirling between two stars, a telltale sign of material swapping places. If complex molecules can make the leap, why not life itself? But the real wild card is tidal forces. The same gravitational stretching that heats planetary interiors could also fracture icy moons or comets, releasing plumes of water and potential life into space. Enceladus in our solar system sprays geysers of water into Saturn's orbit, but in a binary system, those jets might not just fall back as snow. They could be catapulted toward another star's planets, seeding oceans light years apart. Critics argue that radiation would sterilize anything making the journey, but extremophiles on Earth laugh in the face of such assumptions. Deinococcus radiodurans, a bacterium nicknamed Conan the Bacterium, can survive doses of radiation that would liquefy human DNA. Tardigrades, those microscopic water bears, endure the vacuum of space by entering suspended animation. If life can toughen up to survive Earth's extremes, it might thrive in the chaotic transit between binary stars. The implications are staggering. If panspermia works more efficiently in double-star systems, life there might not just exist, it could spread like cosmic wildfire, linking planets in a shared web of biology. Imagine a scenario where life arises once on one lucky world, then leaps to a dozen others via asteroid traffic or stellar winds. Over billions of years, evolution could play out differently on each, creating a menagerie of related but distinct biospheres. We might even find sibling worlds where DNA-like molecules tell the same ancestral story, their shared fingerprints written in the genes of alien flora and fauna. This isn't just speculation, it's a testable hypothesis. Future telescopes could scan binary exoplanet atmospheres for matching biosignatures, hunting for the chemical echoes of shared origins. If we find identical microbial byproducts on worlds light years apart, panspermia might move from sci-fi trope to scientific fact. Until then, binary star systems stand as the ultimate laboratories for this grand idea, places where the universe doesn't just create life but connects it. Planets don't just form, they're sculpted by the environment around them, and in binary star systems, that environment is anything but ordinary. Picture a swirling disk of gas and dust, the raw material of planets caught in the gravitational crossfire of two young stars. In a single star system like ours, this protoplanetary disk settles into a neat, flat plane, giving planets a stable playground to clump together over millions of years. But add a second star and suddenly the rules warp. The disk might tilt, warp, or even fracture under the competing pulls, forcing planetary building blocks into chaotic, unpredictable paths. The first hurdle is sheer survival. Close binary stars, those separated by less than the width of our solar system, can shred their protoplanetary disks before planets even get a chance to form. Their gravitational tug-of-war creates zones of instability where dust grains struggle to stick together without being ripped apart. Some systems counteract this with brute force, disks so massive they withstand the chaos, funneling material into dense spiral arms where planets can coalesce against the odds. Others aren't so lucky. Observations of systems like GG Tau reveal disks with vast inner gaps, regions where the star's gravity has hoarded material for themselves, leaving potential planets starving for building blocks. But when planets do form, their birthplaces can defy imagination. Instead of aligning neatly with their stars' orbits, some worlds end up tilted at extreme angles, even orbiting backward compared to their stellar hosts. These misaligned planets are cosmic rebels, their orbits fossilizing the violent twists of their infancy. In the Kepler-56 system, for example, 3 planets orbit over 30 degrees askew from their star's spin axis, a smoking gun of gravitational mayhem during formation. Binary stars amplify this chaos, their gravitational jostling yanking protoplanetary disks into wonky orientations that planets inherit. Then there's the question of distance. In wide binary systems where stars orbit hundreds of astronomical units apart, planets might form around one star almost undisturbed, until the second star's occasional close pass sends a gravitational shockwave through the system, hurling baby planets into scattered, eccentric orbits. It's like trying to build a sandcastle while a tidal wave rolls in every few millennia. Some worlds get ejected entirely, doomed to wander the galaxy as rogue planets. Others cling to precarious orbits, their paths a testament to the system's turbulent youth. Yet amid this disorder, nature finds workarounds. Circumbinary disks, those encircling both stars, can carve out stable zones where planets form at a safe distance from the stellar chaos. These disks often develop asymmetrical structures, with one side denser than the other, guiding planetesimals into sheltered pockets. The resulting worlds might not follow the neat, circular orbits of our solar system, but they find stability in looping, figure-8 paths that balance the stars' competing tugs. Kepler-34b, a gas giant orbiting 2 sun-like stars, is proof these configurations aren't just theoretical. They're real, and they endure for billions of years. Perhaps the most fascinating twist is how binary stars can actually boost planet formation in unexpected ways. Their gravitational disturbances might trigger density waves in protoplanetary disks, compressing material into clumps that collapse into planets faster than they would in solitude. In some cases, the second star acts like a cosmic stir stick, preventing dust from settling too quickly and extending the window for planet growth. It's a reminder that chaos isn't always destructive sometimes, it's just creative in ways we're only beginning to understand. The takeaway: binary star systems don't just challenge planet formation, they rewrite it. From misaligned orbits to fractured disks, these environments prove that planetary birth is as much about survival as it is about timing and luck. And if worlds can emerge from this gravitational storm, who's to say life couldn't find a way to join them? Among the thousands of exoplanets discovered, Kepler-47c stands out as a cosmic marvel, a world that shouldn't exist yet does. Orbiting 2 stars nearly 5,000 light-years away, this gas giant defied expectations by proving that planets could not only form in binary systems, but also settle into stable orbits within their habitable zones. When astronomers first spotted it in 2012, it wasn't just a new planet, it was a revelation rewriting the playbook on where life might thrive in the universe. What makes Kepler-47c so extraordinary is its delicate cosmic balancing act. Nestled in a system where one star is roughly the size of our Sun, and the other a dim red dwarf just a third as massive, this planet traces a wide, looping path around both. Unlike the chaotic orbits many predicted for circumbinary worlds, its path is almost serene, completing one revolution every 303 Earth days with clockwork precision. Even more astonishing is its position, perched on the inner edge of the system's habitable zone where temperatures could, in theory, allow for liquid water. While the planet itself is likely a gas giant without a solid surface, its moons, if it has any, could be prime real estate for life. Imagine a moon larger than Mars, drifting in the gentle glow of twin suns, its skies painted with swirling auroras from the planet's magnetic field. The discovery forced scientists to rethink fundamental assumptions. Before Kepler-47c, many doubted that binary systems could host planets in stable, life-friendly orbits. The competing gravitational pulls, they argued, would either fling worlds into space or send them spiraling into their stars. Yet here was a planet doing the impossible, a testament to nature's knack for finding equilibrium in chaos. Its existence suggested that circumbinary habitable zones weren't just theoretical. They could be tangible, dynamic regions where energy from both stars combined in unpredictable but life-sustaining ways. But the real intrigue lies in the system's quirks. Kepler-47 stars orbit each other every 7.5 days, creating a rhythmic pulse of light and shadow on any potential moon. For hypothetical lifeforms there, daylight wouldn't follow a simple cycle. Instead, they'd experience shifting patterns of illumination periods where the stars eclipsed each other, casting temporary darkness, followed by surges of combined warmth when both suns blazed together. Photosynthetic organisms might evolve to harvest energy in bursts, storing reserves for the dimmer phases, while animals could develop behaviors synced to these complex light rhythms. Yet Kepler-47c's greatest legacy isn't just its habitability potential, it's the door it kicked open for discovery. Since its detection, astronomers have found dozens of other circumbinary planets, some rocky, some icy, each adding pieces to the puzzle of how binary systems shape their celestial offspring. They've also uncovered a tantalizing pattern. Many of these worlds orbit surprisingly far from their stars, as if nature prefers to build planets where the gravitational fray is less intense. This could mean that stable, life-friendly orbits are rarer in tight binaries, but far from impossible. The lesson of Kepler-47c is clear: the universe delights in proving us wrong. Just when we think we've mapped the limits of habitability, a world like this emerges, glowing defiantly under twin suns, daring us to dream bigger. If life can find a way here, in this dance of gravity and light, where else might it be hiding? In binary systems where one star is a red dwarf, the stakes for potential life aren't just high, they're apocalyptic. These tiny, temperamental stars may be the most common in the galaxy, but they're also cosmic loose cannons, capable of unleashing flares so violent they can scorch entire atmospheres off nearby planets. Imagine a sun that doesn't just shine, it erupts, hurling bursts of ultraviolet and X-ray radiation with the force of millions of atomic bombs. For any world orbiting close enough to stay warm in a red dwarf's feeble glow, these eruptions aren't occasional disasters, they're a constant fact of existence. But here's the twist: life might not just endure this bombardment, it could turn it into an advantage. On Earth, extremophiles like Deinococcus radiodurans thrive in nuclear reactors, repairing their DNA even after radiation doses that would obliterate most organisms. In a binary system with a flare star, evolution could push organisms to develop even wilder defenses. Picture microbes with molecular shields made of manganese complexes, scavenging radiation-induced free radicals before they cause damage. Or multicellular creatures with biofluorescent pigments, converting deadly UV into harmless visible light, turning a threat into an energy source. Some organisms might even mimic Earth's tardigrades, entering suspended animation during flares, only to reanimate when the storm passes. The real wild card is how these adaptations could reshape entire ecosystems. On a planet with frequent flares, surface life might cluster in sheltered niches underwater, beneath ice sheets, or in subterranean networks where layers of rock or water absorb the worst radiation. Forests could evolve bark-rich in UV-blocking compounds, while animals develop reflective exoskeletons or burrowing behaviors timed to stellar activity. Even more intriguing are the atmospheric fixes. A thick ozone layer is Earth's sunscreen, but flare-star planets might need something stronger, hazy hydrocarbon smogs like Titans, or an air rich in sulfur compounds that scatter high-energy light. Over eons, these adaptations could create biospheres utterly alien to our own, where survival isn't about avoiding radiation but metabolizing it. Yet the greatest irony lies in the flares themselves. While they're deadly in the short term, they might also be catalysts for life's origins. Laboratory experiments show that UV radiation can drive the formation of RNA precursors, the building blocks of life. On a young planet bombarded by flares, these violent bursts could have jump-started chemistry in shallow pools, creating concentrated soups of organic molecules between each sterilization event. It's a brutal recipe, but nature has never been gentle. The lesson here isn't just about survival, it's about redefining what's possible. Flare stars don't erase the chance for life, they force it to innovate. And if we ever find organisms thriving under such fury, it'll prove that life isn't a fluke of calm conditions, but a fundamental force of the universe, one that burns brightest where the challenges are greatest. On a planet with two suns, the concept of a day becomes meaningless in the earthly sense. Instead of reliable 24-hour cycles, dawn and dusk arrive in unpredictable bursts, sometimes separated by hours, other times by days, depending on how the stars align in their orbital dance. One moment, the world basks in overlapping daylight as both suns crest the horizon together, flooding the landscape with intense radiation. Then, just as suddenly, one star sets while the other lingers, stretching twilight into eerie, prolonged gloaming. For organisms trying to regulate their biology, this isn't just an inconvenience, it's an evolutionary crucible demanding radical solutions. Take circadian rhythms, the internal clocks that sync earthly life to our planet's rotation. From humans to fruit flies, organisms use light cues to time everything from sleep to metabolism. But transplant those systems to a binary world and they'd collapse in confusion. A plant expecting 12 hours of sunlight might get 4 or 20, its photosynthesis thrown into disarray. Predators coordinating hunts by dawn's light could starve waiting for a morning that never comes on schedule. The very foundations of biology, feeding, resting, reproducing, would need reinvention, yet nature never lacks creativity. Some organisms might abandon rigid cycles altogether, shifting to event-based biology. Instead of waking at a set time, creatures could sync their activity to environmental triggers like temperature shifts as one star's heat fades and the other's dominates. Microbes might enter metabolic overdrive during double daylight phases, stockpiling energy, then switch to low power modes during extended darkness. Trees could evolve leaves that fold or reorient in real time, chasing whichever sun is brightest, turning solar competition into a survival strategy. Others could develop multi-tiered biological clocks like nested hourglasses tracking different stellar rhythms. A creature might have one internal timer attuned to the larger star's 18-hour orbit, another calibrated to the smaller star's 6-hour loop, combining them like interlocking gears to anticipate light patterns. Some biologists speculate these organisms might experience something alien to us, polyphasic rest, sleeping in short bursts whenever darkness briefly falls, rather than consolidating sleep into one block. The real marvels would be the adaptations we can't yet imagine. Perhaps organisms would evolve predictive biology, using subtle gravitational cues to sense upcoming alignments before light changes. Or communal lifeforms might share timing signals like coral reefs that pulse with collective bioluminescence to coordinate feeding under erratic skies. In a universe where binary stars are the norm, life wouldn't just endure the chaos, it would dance to its rhythm, rewriting the rules of time itself. In the cosmic theater of binary star systems, time unfolds on scales that dwarf human comprehension, where one star might burn steadily for billions of years while its companion races toward an explosive demise. Imagine a world where the sky is dominated by two suns, one a youthful yellow star like our own, the other a massive blue giant destined to live fast and die young. For any life clinging to planets in this system, the ticking clock isn't just about survival, it's about adapting to a cataclysm that could rewrite the rules of existence. Take a pair like Sirius A and B, a blazing white main sequence star paired with a dense white dwarf. Today, Sirius B is a ghostly ember, but billions of years ago, it was the larger, hotter star of the two, shining brilliantly before collapsing into its current state. Any planets orbiting this duo would have witnessed a stellar metamorphosis, the violent death throes of a giant shedding its outer layers in a planetary nebula, while its core contracted into a tiny, searing hot remnant. The question isn't just whether life could survive such an event, it's whether it could emerge in the first place, then endure the chaos that followed. When a star exhausts its nuclear fuel, the consequences depend on its size. A sun-like star swells into a red giant, engulfing inner planets and scorching others with intense radiation before leaving behind a white dwarf, a dense, Earth-sized cinder glowing with residual heat. In a binary system, this transformation could leave the surviving star to illuminate the corpse of its former partner, casting eerie, shifting light over any remaining world. Planets once bathed in warmth might freeze as the white dwarf cools, their atmospheres condensing into snow. Yet life, if it exists, could retreat underground, tapping geothermal energy or the white dwarf's lingering heat. More dramatic still is the fate of massive stars. If one star in a binary pair is heavy enough, it won't fade quietly, it'll explode as a supernova, blasting its companion with radiation and shock waves. For nearby planets, the burst would be apocalyptic, stripping atmospheres and boiling oceans in an instant. But at a safer distance, worlds might weather the storm. The supernova could even seed the system with heavy elements, enriching future planets with the building blocks of life. And if the core collapses into a neutron star or black hole, the surviving star's orbit would warp into a frantic dance around this new gravitational monster, its planets subjected to extreme tides and particle jets. The real wild card is timing. Stars like red dwarfs burn for trillions of years, far longer than the universe's current age. Pair one with a short-lived giant, and life might arise only after the explosive star has died, evolving in the calm glow of the smaller survivor. Alternatively, in systems where both stars are similar in mass, their synchronized aging could mean their habitable zones shift in tandem, offering life a moving sanctuary as each star transitions through its life cycle. What's clear is this: in binary systems, stellar death isn't always the end. It's a transformation, one that could forge new niches for life even as it destroys others. From the radioactive fury of a supernova to the slow fade of a white dwarf, these systems remind us that habitability isn't a permanent state. It's a fleeting window, and life, if it's clever enough, might just find a way to keep that window open. Plants on Earth have mastered the art of turning sunlight into sustenance, but on a planet with two suns, that skill would need a radical upgrade. Instead of relying on the steady glow of a single star, alien flora would face a dazzling yet chaotic light environment, where the spectrum shifts unpredictably between the harsh blue of a younger sun and the deep red of an aging companion. Survival here wouldn't just mean adapting to different wavelengths, it would mean evolving systems that could switch between them on the fly, or even harvest both at once. One possibility is layered pigments. Think of leaves not as uniform green panels, but as stacked solar arrays, each tier tuned to a different star's output. The upper layers might bristle with molecules optimized for shorter, high-energy wavelengths from a blue-white sun, while deeper tissues absorb the lingering infrared of a cooler red dwarf. Earth's plants already hint at this strategy. Shade leaves often pack more chlorophyll B to catch low-light spectra missed by their sunbathed counterparts. On a binary world, this division could be extreme, with canopy and understory pigments coexisting in the same organism, flipping dominance as the stars cycle overhead. Then there's the potential for wavelength switching systems, biological machinery that reconfigures itself based on which star dominates the sky. Imagine pigments that shift shape when struck by specific light frequencies, like a photosynthetic chameleon. Some Earth bacteria use retinal proteins to convert light into energy without chlorophyll, a trick binary plants might expand upon. Their leaves could transition from blue absorbing during one star's peak to red harvesting when the other rises, with transitional states blending both. Over generations, this adaptability might hardwire into stunning diversity. Groves where neighboring plants specialize in opposing stars, their hues clashing like rival teams under the same sky. But the real game changer could be simultaneous multi-spectrum harvesting. Earth's photosynthesis wastes much of the sun's green light, reflecting it away. Alien plants might evolve compound systems pairing chlorophyll-like molecules with exotic counterparts that capture neglected wavelengths, turning wasted photons into bonus energy. Some could even borrow from deep-sea vents, where microbes use sulfur-based chemistry to thrive in darkness. Combine that with stellar light, and you get hybrids that photosynthesize and chemosynthesize, switching modes as flares or eclipses alter their world's energy flow. The fallout of such adaptations would ripple through entire ecosystems. Pollinators might evolve UV vision to spot flowers keyed to one star's peaks, while nocturnal feeders track blooms activated by the other's twilight. Forests could develop stratified canopies, with top layers optimized for the brighter sun and lower ones filtering residual light from its dimmer twin. And if these plants move, they might tilt or reposition leaves like living satellite dishes, chasing the optimal angle as the stars slide across the sky. What's thrilling isn't just the variety of solutions, but their implications. If life can engineer such dazzling versatility under twin suns, it reshapes how we hunt for biosignatures. Instead of scanning exoplanets for Earth like chlorophyll, we might need to search for mixed chemical fingerprints, or even rhythms in surface albedo as alien flora pivot between stellar light sources. The universe's palette for life isn't limited to green. Under two suns, it could be rainbow. Predators on a world with two suns face a sensory nightmare. How do you stalk prey when the light never behaves the same way twice? Under Earth's single sun, shadows fall predictably, giving hunters the advantage of ambush and prey the chance to flee. But in a binary system where stars rise and set out of sync, shadows split and swirl unpredictably across the landscape. One moment, a predator might lurk in the deep shade of a boulder. The next, a second sun crests the horizon, flooding its hiding spot with light and exposing it to alert herbivores. Survival here would demand evolutionary innovations unlike anything on our planet. Take camouflage, for example. On Earth, creatures evolve colors and patterns to blend into static backgrounds, a peppered moth matching tree bark or a desert lizard mirroring sand. But on a planet with shifting double daylight, effective camouflage would need to be dynamic, changing in real time as illumination shifts between the stars' contrasting hues. Some organisms might develop chromatophores, specialized cells that expand or contract to alter skin tone, like an octopus, but tuned not just to color, but to intensity and even shadow angles. Picture a six-legged predator whose hide darkens to match the red dwarf's crimson glow when that star dominates, then pales to reflect the yellow sun's brilliance when it rises. Prey, meanwhile, could evolve iridescent scales that scatter light unpredictably, creating a disorienting shimmer as they dart between overlapping pools of starlight. Hunting strategies would warp just as dramatically. Earth's predators rely on predictable cycles of light, and dark lions hunt at dawn when prey are silhouetted, while owls leverage nighttime silence. But in a binary system, dawn might last for days as one sun lingers below the horizon while the other circles low. Predators could abandon circadian rhythms entirely, becoming opportunistic generalists that strike whenever shadows or sensory conditions briefly favor them. Some might develop multimodal senses, switching between vision tuned to each star's spectrum. A pack hunter's eyes could have dual retina layers, one optimized for the blue star's harsh light, another sensitive to the red dwarf's infrared glow, allowing them to track prey seamlessly as dominance shifts between suns. Prey wouldn't just hide, they'd weaponize the light chaos. Herd animals might evolve synchronized movements, creating strobing patterns of reflected light to dazzle predators during double daylight phases. Others could develop thermal masking, with body temperatures adjusting to match ambient heat from whichever star is dominant, rendering them invisible to infrared sensing hunters. And in a twist straight from sci-fi, some prey might even exploit stellar eclipses, timing mass migrations to moments when both suns align and plunge the landscape into temporary darkness, slipping past predators reliant on visual cues. The most radical adaptations, though, could lie in sensory trade-offs. With light conditions in constant flux, some creatures might abandon vision altogether in favor of seismic sensitivity, feeling vibrations through specialized pores as predators approach across vibrating terrain. Others might communicate through bioluminescent pulses, using the ever-changing background light to mask their signals from hunters. Evolution in this environment wouldn't favor specialists, but shapeshifters, organisms so adaptable they rewrite their survival playbook by the hour. What emerges isn't just a new ecosystem, but a new logic of existence. In binary star systems, predator and prey don't engage in a static arms race, they dance on a kaleidoscopic battlefield where the rules change with every rotation of the heavens. And the winners, they won't be the strongest or fastest, but the most ingeniously flexible life forms that treat chaos not as a threat, but as their greatest ally. For an intelligent species evolving under twin suns, the sky isn't just a backdrop, it's the foundation of their entire worldview. Unlike Earth civilizations, which calibrated their earliest myths and calendars to the steady rhythms of a lone sun, these beings would navigate a celestial ballet where time and light behave in ways we'd find surreal. Imagine a culture where the concept of noon is fluid, where eclipses happen daily as one star passes in front of the other, and where shadows sometimes point in two directions at once. Their myths wouldn't speak of a single sun god riding a chariot across the sky, but of dueling deities locked in an eternal embrace, their conflict and harmony dictating the ebb and flow of life below. Calendars in such a society would be masterpieces of complexity. Earth's years and months stem from simple orbital mechanics, but a binary system's overlapping stellar cycles would demand timekeeping that accounts for multiple rhythms. Perhaps they'd track great years spanning centuries, marking the slow precession of their stars' orbits, while shorter cycles note the intervals between double sunrises. Festivals might sync to rare celestial alignments, moments when both stars eclipse simultaneously, plunging the world into eerie twilight and sparking rituals to appease whatever forces govern their unstable heavens. Even daily life could revolve around these patterns, architecture designed to channel shifting light angles, or agriculture timed to exploit fleeting periods when both suns bathe fields in ideal wavelengths for growth. Technology, too, would follow a divergent path. With astrophysics baked into their cultural DNA, these civilizations might leapfrog our own understanding of orbital mechanics. While humanity spent millennia believing Earth was the universe's center, a binary world astronomer would grasp the principles of gravitational interplay from their first observations. Their mathematicians could discover chaos theory centuries earlier, intuiting how tiny perturbations alter complex systems. After all, their ancestors farmed and navigated by stars that never moved predictably. Space travel might prioritize stability over speed, with navigation systems calculating ever-changing gravitational gradients rather than static trajectories. Even their energy grids could harness stellar flux, developing adaptive solar panels that switch between absorbing blue and red wavelengths as light conditions shift. The real marvel lies in the philosophical shifts this environment would forge. Our species framed existence in binaries, day and night, summer and winter. But a mind shaped by twin suns might think in spectrums and probabilities, comfortable with ambiguity. Their art could revel in iridescence, capturing the way colors morph under blended starlight. Their music might mimic the harmonic resonance of orbital cycles, with compositions structured like celestial mechanics, repeating yet never identical. And their greatest scientific breakthroughs, they'd likely center on duality, wave-particle understanding emerging not as a paradox, but as an obvious truth mirroring their double-lit world. Perhaps most strikingly, their drive to explore the cosmos would carry unique urgency. A culture reared under unstable heavens would know their world's delicate balance could shatter, whether from stellar evolution, gravitational shifts, or the eventual death of one sun. This existential awareness might propel them toward interstellar travel faster than our own civilization, not just out of curiosity, but as a survival imperative. After all, when your sky reminds you daily that nothing lasts forever, the stars aren't just destinations, they're lifelines. Advanced civilizations in binary star systems wouldn't simply adapt to their twin sun environment, they'd reshape it. Picture an alien society harnessing the combined energy of two stars by constructing a Dyson swarm not around one sun, but both. These megastructures, vast arrays of orbiting solar collectors, could form intricate double-armed patterns, balancing between the stars' competing gravitational pulls to maximize energy capture. Unlike single star systems where collectors follow neat concentric orbits, a binary Dyson swarm would require staggering engineering precision, with individual satellites adjusting their trajectories in real time to avoid destabilizing collisions as the stars dance through space. One solution might involve Lagrange point engineering, those gravitational sweet spots where forces between the stars cancel out. In the L1 point directly between both stars, a civilization could anchor a central control hub, coordinating thousands of energy-harvesting platforms that fan out along stable orbital pathways. The L4 and L5 points, 60 degrees ahead and behind each star's orbit, could host massive manufacturing stations, using the zone's stability to produce and launch new swarm components. Telescopes like James Webb might detect such structures indirectly through unusual infrared signatures, not the uniform waste heat of a single star Dyson sphere, but fluctuating thermal patterns that pulse in sync with the binary's orbital period. But why stop at energy collection? A sufficiently advanced species might transform the entire system into a cosmic art piece. Imagine stellar mirrors positioned to create dazzling light shows, perhaps for cultural celebrations or interstellar communication. By carefully angling enormous reflective surfaces near one star, they could project shifting patterns onto the atmosphere of a neighboring planet, or even beam focused light pulses toward other star systems as a form of slow but mighty galactic Morse code. The most ambitious projects could involve stellar engineering on a breathtaking scale. One star in the pair might be artificially slowed or sped up to create more stable planetary orbits, its mass subtly adjusted using particle beams or controlled fusion. Alternatively, a civilization might induce one star to feed its partner through constructed plasma conduits, balancing their lifespans to extend the system's habitable epoch. Such tampering would betray itself through abnormal stellar spectroscopy, sudden chemical imbalances or rotation rates that defy natural models. For astronomers hunting these technosignatures, the key lies in anomalies. Binary systems already exhibit complex physics, but certain irregularities would scream artificial. Unusual transits where something blocks starlight with unnatural symmetry, or stars whose energy output remains suspiciously stable despite their turbulent interactions. Even gravitational wave detectors might one day pick up the rhythmic hum of massive machinery, subtly altering a binary's orbital resonance. The beauty of this search is that binary systems offer built-in magnifying glasses for detection. When two stars eclipse each other from our viewpoint, any orbiting megastructures would cast additional shadows or distort the light curve in telltale ways. And if a civilization is intentionally signaling others, the eclipses themselves could be used as a natural amplifier. Imagine synchronized energy pulses beamed precisely when the stars align from Earth's perspective, turning a routine astronomical event into a cosmic semaphore. What makes these possibilities so electrifying isn't just the scale of engineering involved, it's the glimpse into how intelligence might express itself when born into celestial chaos. Where we see instability, they may see opportunity, bending the furious energy of twin suns to purposes we're only beginning to fathom. In the cosmic theater of binary star systems, few events would rival the spectacle of a double eclipse, a moment when one sun slips behind the other, plunging the world into sudden, profound darkness. Unlike Earth's fleeting solar eclipses, these occultations could last hours or even days, unfolding with a rhythmic precision dictated by the star's orbital dance. For any life forms clinging to these worlds, these aren't just celestial shows. They're existential turning points, shaping biology in ways that defy earthly logic. Consider the sheer sensory whiplash on a planet like Kepler-16b, where twin suns eclipse each other every 21 days. Daylight might vanish without warning as the larger star blocks its smaller companion. Temperatures could plummet by dozens of degrees in minutes, forcing life to adapt to rapid fire cycles of scorching heat and icy stillness. Some organisms might treat these eclipses like a biological snooze button, microbes slowing their metabolism to weather the cold, or plants folding photosynthetic tissues to conserve energy until light returns. Others could evolve eclipse-triggered behaviors, like creatures on Earth syncing reproduction to full moons. Imagine herds of alien grazers stockpiling nutrients before an eclipse, then entering torpor as darkness falls, their heartbeats slowing to near zero until the stars realign. The darkness itself could become an ecological catalyst. On Earth, nocturnal species exploit the cover of night to hunt or avoid predators. But in a binary system, eclipses would create temporary nights at irregular intervals, perfect opportunities for stealthy predators to ambush prey adapted to constant daylight. Evolution might favor creatures with bioluminescent lures, flashing in the sudden dark to attract disoriented prey, or infrared vision to track warmth against the cooling terrain. Even plants could get in on the act. Some might time seed dispersal to eclipses, using the temperature drop to trigger pods to burst, scattering offspring into winds calmed by the absence of solar heating. Then there's the question of rhythm. Earth's life thrives on predictable cycles. Day follows night, winter follows summer. But in systems where eclipses arrive chaotically, biology might abandon rigid clocks altogether. Instead of circadian rhythms, organisms could rely on environmental cues, shifts in atmospheric pressure as eclipses approach, or subtle changes in starlight polarization that hint at impending darkness. Some might even develop eclipse memory, with nervous systems primed to anticipate the next event based on past intervals, like internalized celestial arithmetic. The most radical adaptations might be chemical. For species bathed in constant radiation from two stars, eclipses could offer a rare respite, a chance to repair DNA damage without the usual bombardment of ultraviolet light. Organisms might stockpile protective pigments during bright phases. then activate repair enzymes the moment darkness falls, turning eclipses into microscopic maintenance windows. Others could use the cold to trigger cryobiosis, a state of suspended animation that lets them ride out the harsh transition unscathed. But the real marvel lies in how these events could shape intelligence. A civilization rising under twin suns would perceive eclipses not as anomalies but as foundational to their cosmology. Their myths might speak of a great serpent swallowing the sky or a divine balance between light and shadow. Their technology could harness eclipse cycles, building solar grids that store energy in anticipation of darkness, or engineering crops that flower exclusively during these dim intervals to avoid herbivores. Even their art could mirror the phenomenon, music with motifs that vanish and reappear, or paintings that change hue under different stellar lights. What emerges is a revelation. Eclipses in binary systems aren't disruptions. Their punctuation marks in the story of life, intervals of darkness that carve out niches, drive innovation, and remind us that biology, no matter how alien, always finds a way to dance with the stars. While gas giants in binary star systems often steal the spotlight, their moons could be the unsung heroes of cosmic habitability, hidden oases cradled in the protective embrace of their massive hosts. Picture a world like Europa or Titan, but orbiting a Jupiter-like planet that itself circles twin suns. Such a moon wouldn't just face the ordinary challenges of tidal heating and faint sunlight. It would endure the gravitational chaos of its binary stars. Yet here's the twist: that very chaos might forge the perfect refuge. A gas giant's magnetic field acts like a planetary force field, deflecting deadly stellar radiation and solar winds. In single star systems, this shields moons like Europa from their sun's worst outbursts. But in a binary system where radiation belts from two stars collide, the giant planet's magnetosphere becomes a life-saving bunker. Moons nestled within this invisible barrier could enjoy a double layer of protection, sheltered not just from one star's flares, but from the crossfire of both. Tidal forces add another layer of possibility. A moon orbiting close to its gas giant would experience constant gravitational kneading, flexing its interior until subterranean oceans churn beneath icy crusts. On Earth, hydrothermal vents in pitch-black depths teem with life. On these exomoons, similar ecosystems could thrive, warmed not by sunlight but by the relentless friction of their host planet's pull. The beauty of this setup: while binary stars might scorch or freeze a planet's surface, tidal heating could maintain liquid water underground for eons, regardless of the stellar chaos above. Then there's the climate buffer. Gas giants are cosmic thermal sponges, absorbing and redistributing heat across their sprawling atmospheres. A moon parked in the right orbit might tap into this stability, its temperature moderated by the giant's slow-release warmth. Even if the twin suns' combined light fluctuates wildly, the moon's climate could remain oddly temperate, like a ship riding out a storm in the lee of an island. The real kicker: diversity. A single gas giant might host multiple moons, each with its own niche. One could be an ice world with a subsurface sea, another a methane-soaked labyrinth of cryovolcanoes, and yet another a rocky outcrop with just enough atmosphere to trap heat. In a universe where binary stars often seem hostile to life, these moons could form an archipelago of habitability, each a potential incubator for biology as unique as the stars that light their skies. What makes this scenario so compelling is how it flips the script. We often imagine life clinging to planets, struggling against stellar extremes, but moons, they've got planetary bodyguards. In the cosmic drama of binary systems, they might just be the safest seats in the house. Science fiction has painted binary star systems as both breathtaking and brutal, from the twin sun vistas of Tatooine in Star Wars to the floating mountains of Pandora orbiting Alpha Centauri. But how much of this cinematic spectacle aligns with real astrophysics? The answer lies somewhere between poetic license and genuine cosmic phenomena. Take Tatooine's iconic double sunset. While visually stunning, the physics isn't far off. Planets in wide binary systems can indeed experience staggered sunsets as one star dips below the horizon before the other. Kepler-16b, a real gas giant dubbed the Tatooine planet, orbits two stars, proving the concept isn't purely fantasy, but Hollywood often glosses over the chaos. Luke Skywalker's homeworld shows a stable desert climate, yet real binary planets would face wild temperature swings, unpredictable daylight cycles, and gravitational stress that could fracture tectonic plates over time. Then there's Pandora from Avatar, nestled in the Alpha Centauri system. While the film nails the triple-star setup, Alpha Centauri is actually a trinary system. It simplifies the orbital mechanics. Pandora's bioluminescent jungles thrive under a single large star, with the smaller companions treated as distant backdrops. Reality would be messier. In a trinary system, planets often get ejected or endure extreme seasons as stellar gravities compete. The movie's floating Hallelujah Mountains, explained by unobtainium's anti-gravity properties, are pure fiction, but the idea of exotic geology isn't. Real binary planets could experience tidal forces so intense they trigger volcanic hyperactivity or create vast tidal bulges, warping crustal plates into surreal landscapes. Where sci-fi often exaggerates is in the sheer livability of these worlds. Films rarely show the atmospheric stripping from stellar flares, the lethal radiation showers, or the centuries-long winters some orbits would impose. Even the color palettes are idealized. Dual starlight would mix unpredictably, casting murky, shifting hues rather than the golden glow of Tatooine or Pandora's ethereal blues. Yet some tropes hold up. The idea of eyeball planets, tidally locked worlds with a perpetual dayside and frozen nightside, is grounded in real astrophysics, though few films explore their true extremes. The biggest divergence, timekeeping. Sci-fi civilizations somehow share Earth's 24-hour rhythms, but real binary system cultures would need calendars tracking multiple stellar cycles, with days and years losing all familiar meaning. Imagine a society where ages are measured in eclipses rather than birthdays, or where navigation relies on deciphering the ever-shifting angles of twin shadows. These nuances rarely make the screen, but they're where the true drama of binary life lies, not in the skies we imagine, but in the ones that defy imagination entirely. When scanning the cosmos for signs of extraterrestrial intelligence, astronomers don't just aim their telescopes at any star, they prioritize binaries. The logic is simple. If double star systems dominate the galaxy, as observations suggest, then any advanced civilization is statistically more likely to emerge in one. But there's more to it than just playing the odds. Binary stars create unique cosmic laboratories where the challenges of survival might accelerate technological innovation. Picture a civilization that masters energy harvesting under wildly shifting light conditions, or one that develops precision orbital engineering to stabilize their world's chaotic trajectory. These aren't just survivors, they're cosmic problem solvers, the types of beings whose solutions might leave detectable signatures across interstellar space. One of the most ambitious efforts to eavesdrop on binary systems is the Breakthrough Listen initiative, which allocates significant telescope time to stars like Kepler-47. Using instruments like the Green Bank Telescope and Parkes Observatory, the project scans for narrowband radio signals, artificial transmissions that stand out against natural cosmic noise. Binary systems are prime targets because their complex gravitational environments could inspire civilizations to develop powerful communication systems, perhaps using their star's orbital motion to sling high-energy pulses across the galaxy. The Very Large Array in New Mexico has also joined the hunt, monitoring eclipsing binaries for laser flashes that might coincide with stellar alignments, a potential alien lighthouse effect. Then there's the role of planetary transits. In systems like Kepler-16, where planets pass in front of both stars from our viewpoint, astronomers watch for anomalies in light curves that could hint at megastructures. The SETI Institute's laser SETI program deploys all sky cameras tuned to detect nanosecond laser pulses, ideal for catching fleeting signals from worlds where day and night arrive unpredictably. Meanwhile, the Transiting Exoplanet Survey satellite TESS flags binary systems with unusual dimming patterns, some of which might not be planets at all, but artificial constructs like orbiting solar collectors. But why focus so intensely on binaries? Beyond their abundance, these systems force life to contend with extremes, and overcoming extremes demands creativity. A civilization that stabilizes its climate despite tidal upheaval or harnesses energy from two erratic stars might develop technologies visible across light years. Their very survival could depend on broadcasting their presence, whether to warn others of stellar dangers or to seek alliances in a turbulent cosmos. The search isn't just about finding life, it's about finding life that's triumphed over chaos. And if such civilizations exist, their ingenuity might shine brighter than any star. Detecting Earth-like planets in binary star systems has always been a needle in a haystack challenge, but the next generation of telescopes is about to turn that haystack into a spotlight. Leading the charge is NASA's Habitable Worlds Observatory, or HWO, slated for launch in the 2030s. Unlike its predecessors, this space-based observatory won't just hunt for planets. It's designed to dissect their atmospheres with surgical precision, searching for the chemical fingerprints of life. And here's what sets it apart. HWO's coronagraph will be fine-tuned to block the blinding glare of two stars simultaneously, revealing faint, Earth-sized worlds that current telescopes miss. Imagine analyzing the atmosphere of a planet where oxygen levels spike during double daylight phases, or where methane concentrations pulse in sync with stellar eclipses. Those are the kinds of biosignatures HWO could trace back to alien biology. But HWO won't work alone. The European Extremely Large Telescope, or ELT, rising from Chile's Atacama Desert, will complement it with groundbreaking ground-based observations. With a mirror stretching 39 meters across, wider than a blue whale is long, ELT's adaptive optics can cancel out the atmospheric blur that plagues Earth-bound telescopes. Its spectrometer will break starlight into wavelengths so fine, it could detect chlorophyll on a distant exoplanet's forests, or whatever alien equivalent evolved under twin suns. Picture this, a team of astronomers in 2045, comparing HWO's space-based data with ELT's surface observations, cross-referencing oxygen spikes with vegetation-like reflectance patterns. For the first time, we might not just find a planet in a binary system's habitable zone, we'd smell its air. The real game-changer, though, could be quantum dot astronomy. Still in experimental stages, this tech replaces traditional telescope mirrors with sheets of nanoparticles that bend light in ways conventional optics can't. Future versions might resolve planetary surfaces directly, transforming blurry dots into continents and oceans. In a binary system, this could reveal climate patterns sculpted by competing stars, like hurricane belts pinned where two stellar winds collide, or deserts that bloom only when both suns align. Yet the biggest discoveries might come from anomalies we can't yet predict. When the James Webb Space Telescope launched, no one expected it to find carbon dioxide on a world like WASP-39b, yet there it was. HWO and its successors will likely rewrite the rules just as dramatically. Maybe we'll spot industrial pollutants in an exo-atmosphere, or seasonal blooms of photosynthetic pigments tuned to dual starlight. Or perhaps the biosignatures will be utterly unrecognizable gases that don't exist on Earth, forged by life playing by alien rules. What's certain is this: within our lifetimes, the question of life in binary systems will shift from speculation to hard data. And when that data arrives, it won't just tell us if we're alone, it'll show us how wildly creative the universe can be when it writes the story of life twice. Terraforming a planet under two suns isn't just an engineering challenge, it's an ethical minefield. On one hand, binary star systems offer untapped resources, double the stellar energy, gravitational interactions that could be harnessed for slingshot travel, and exotic elements forged in their turbulent orbits. But on the other, these chaotic environments pose risks we're only beginning to grasp. What happens if we pour centuries of effort into reshaping a world, only for an unpredictable stellar flare or orbital shift to undo everything? The debate isn't just about feasibility, it's about responsibility to future generations, to any native life we might displace, and to the cosmic balance we'd irrevocably alter. Consider the allure first. A planet orbiting twin stars could become the ultimate energy hub, with solar farms designed to capture light from both suns in shifting configurations. The very instability that makes these systems hazardous might also make them fertile ground for innovation. Tidal forces could be tapped for geothermal power, while Lagrange points between the stars might serve as natural way stations for interstellar travel. And let's not forget the scientific payoff. Terraforming a binary world would force us to master climate control on a scale we've never attempted, potentially yielding breakthroughs to heal our own planet's ecosystems. Yet the hazards are staggering. Binary stars are prone to violent outbursts, flares that could strip away an atmosphere we've painstakingly cultivated, or gravitational surges that might destabilize a terraformed world's orbit over millennia. There's also the haunting question of native life. Even if a planet appears barren, subsurface microbes or chemical precursors to biology could exist in niches we've yet to detect. Introducing Earth-like conditions might annihilate these fragile systems before we've had a chance to study them, committing the same colonial mistakes we've made throughout history, just on a cosmic scale. Ethical frameworks struggle to keep pace. Current space law, like the Outer Space Treaty, forbids claiming celestial bodies as sovereign territory but says little about ecological stewardship. Would diverting comets to supply water to a binary planet violate interstellar conservation principles? If we trigger a greenhouse effect to warm a frozen world, only to destabilize its climate further, do we have a moral obligation to intervene indefinitely? These aren't hypotheticals, they're decisions with trillion-year consequences. Perhaps the answer lies in gradations. Instead of full terraforming, we might opt for paraterraforming, sealing habitats beneath domes or subterranean networks, leaving the broader environment untouched. Or we could prioritize binary systems with older, calmer stars, minimizing the risk of cataclysmic eruptions. But even these compromises carry weight. Every choice stakes a claim on the galaxy's future, and unlike Earth, there's no undo button in space. The deeper we delve, the clearer it becomes. Binary systems aren't just new frontiers. They're mirrors, forcing us to confront who we are as a species: explorers or conquerors, stewards or opportunists. The stars won't judge our decisions, but the universe will remember them. The universe has a way of turning chaos into cradle, and nowhere is that more evident than in the swirling dance of binary star systems. These cosmic duos, once dismissed as hostile to life, now stand as testament to nature's relentless ingenuity. From planets tracing figure 8 orbits to microbes evolving under shifting spectra of starlight, the possibilities here stretch beyond earthly imagination. Life under twin suns wouldn't just adapt, it would rewrite the rules, crafting biological solutions so radical they'd make our extremophiles look mundane. Consider the sheer diversity of habitats these systems could host. A tidally locked moon might harbor subsurface oceans warmed by gravitational friction, while a circumbinary planet's twilight zone blooms with black-leafed flora harvesting light from both stars. Predators could sport dynamic camouflage, shifting hues to match whichever sun dominates the sky, while intelligent beings design calendars tracking not just orbits but the resonant harmonies between them. Even the sky would defy expectations, auroras rippling from dual stellar winds, eclipses painting ephemeral shadows across continents, and constellations that reconfigure as the stars wheel through their celestial waltz. The implications ripple outward. If life can thrive in such turbulence, then the galaxy's habitable real estate just exploded. Binary systems outnumber solitary ones, meaning the cosmos could be brimming with biospheres far stranger than anything we've dreamed. And if intelligence arises here, its very foundation would be different, shaped by unstable heavens, tempered by extremes, and likely wielding technologies forged in the crucible of duality. So when we gaze at the night sky, let's not just look for familiar stars. Let's imagine the ones we can't see, the pairs twirling in the dark, their planets bearing witness to double sunrises, their histories written in light and shadow. And let's wonder, when humanity finally detects that first alien signal, will it come from a world like ours, serenely orbiting a single star? Or will it pulse from a planet where the sky burns with two suns, a place where life didn't just survive the chaos, it learned to sing with it?